So, welcome to module 26. In this module, we will discuss the joint movement generating function of random vectors and also the equality in distribution. We have already dealt with this topic for random variables in real line, and I will repeat the same concept for random vectors in p-dimensional Euclidean space. So, to see the setup, so suppose x is x1, x2, xp, which is a p-dimensional random vector, and suppose my set A is collection of all those t1, t2, tp in Rp such that absolute value of e to power summation ti xi has a finite expectation. So, that is, this is a set where this quantity exists or is finite. Now, I define the function mx from A to R by mxt, which is expected value of summation I is equal to 1 to p ti xi, where t is equal to t1, t2, tp belongs to A, because A is the set where this quantity is finite. So, I call this function to be the movement generating function of random vector x. Now, if you recall the definition of movement generating function for real random variables, it was if p was 1, then mxt was defined as expected value of e to power tx, and there also we had defined a set A where this quantity is finite. So, if you take p is equal to 1, you can see that these two definitions coincide. So, it is in a sense obvious generalization of definition of movement generating function from R1 to Rp. So, this function is called the movement generating function of random vector x. Now, let us see some of the immediate observations from the definition. So, note that my mxt is defined as expected value of e to power summation I is equal to 1 to p ti xi, right, where vector t is in the set A. Note that if I take vector t to be 0, so that means all these ti's are 0, then it becomes e to power 0, which is 1. So, expected value 1 is 1. So, mx0 is 1, and this property was possessed by univariate movement generating function as well. So, that way the set where this quantity is finite is non-empty, and that is what it says, A is non-empty. Now, suppose x is x1, x2, xp, and suppose x1, x2, xp are independent. So, for A is equal to A1, A2, AP, let us try to define a random variable y, which is a linear combination of x1, x2, xp. So, I define y to be summation I is equal to 1 to p ai xi. Let us try to see what is the movement generating function of y. Y is a real random variable. Note that this is a real random variable. So, my at the point t, so this will not be a vector t, it should be a point t. Myt is expected value of e to power ty, and this is nothing but y. So, this is expected value of e to power ty. Now, e to power t summation I is equal to 1 to p ai xi is same as expected value of product I is equal to 1 to p e to power t ai xi. Now, since xi's are independent, so expectation of product of functions of xi's would be same as product of expectation of corresponding functions. So, this is because of the fact that xi's are independent. But now, if I try to look at this quantity, this is nothing but movement generating function of xi at the point tai. So, that is what we write it down over here. So, if x1, x2, xp are independent, then movement generating function of linear combination of xi's can be written as product of movement generating function of xi's at the point tai's. Now, let us take if all ai's to be 1, then what it says is movement generating function of sum of random variables is same as product of movement generating function of individual movement generating function, because then I will take ai to be 1. So, this is what the second observation says. In particular, if z is I is equal to 1 to p xi, so that means all ai's are 1, then mzt is same as product I is equal to 1 to p mxit, where t is in real line. So, what it says is that the MGF of sum of independent random variables is same as the product of marginal MGFs. In fact, later we will see that converse is also true. If the movement generating function, joint movement generating function is same as product of marginals, then one can conclude that x1, x2, xp are independent. But that result we will do later. But let us try to see few more things. So, let us see what is mxt. mxt is same as expected value of e to power summation I is equal to 1 to p ti xi, which is same as expected value of product I is equal to 1 to p e to power ti xi. Now, let us say x is x1, x2, xp. Now, what I do is I put the argument Tp to be 0. Let us try to put the argument Tp to be 0. Then in this product, that means e to power 0 xi would come, that would contribute 1. So, it would become product I is equal to 1 to p minus 1 e to power ti xi, and that is nothing but movement generating function of x1, x2, xp minus 1 at the point t1, t2, tp minus 1. So, that is what it says if I take x as x1, x2, xp and y as x1, x2, xp minus 1, and if I have to get the movement generating function of y, which is x1, x2, xp minus 1, what I do is in the joint MGF of x1, x2, xp, I put Tp is equal to 0. So, then I get expected value of product I is equal to 1 to p e to power ti xi, which is nothing but movement generating function of x at the point t1, t2, tp minus 1. So, what it suggests is one can obtain the marginal MGFs from the joint MGF by taking the argument of unwanted variable in joint MGF to be 0, and that is what we did over here. So, xp was the unwanted variable I wanted because MGF of x1, x2, xp minus 1. So, I put the argument Tp is equal to 0 to get the movement generating function of x1, x2, xp minus 1. So, for example, if I put all other arguments as 0 except the ith argument in the joint MGF, I get the movement generating function of xi, which is again clear from here because all others are put 0. So, they will contribute 1 and e to power ti xi would come. Similarly, if I put all others to be 0 except ti and tj, all others would contribute 0. So, I will get x to e to power ti xi, e to power tj xj, which is nothing but movement generating function of xi and xj at the point ti and tj. So, what you need to do is to get the marginal MGFs, you put the arguments of unwanted variables to be 0 in the joint MGF. Now, also note that if x1, x2, xp are independent, then mxt is same as expected value of e to power t summation I is equal to 1 to p xi, which is same as expected value of product I is equal to 1 to p t xi, but xi's are independent. So, expected value of this product would be same as product of expectations. This is because xi's are independent, and this is nothing but mxi ti. So, what it suggests is that if x1, x2, xp are independent, then joint MGF is same as product of marginal MGFs. We will see that converse of this is also true. That means, if joint MGF is same as product of marginal MGFs, then x1, x2, xp would be independent. But before that, let us do this result. We did similar result in the case of real random variable. So, suppose your joint MGF is finite in a rectangle minus a to a. So, suppose your MGF is finite in a neighborhood of 0, the point 0. Then mxt possesses partial derivatives of all orders in minus a to a. Furthermore, for any non-negative integers k1, k2, kp, expected value of mod of x1 to power k1 to mod of xp to power kp is finite. Not only that, one can get expected value of x1 to power k1, xp to power kp by differentiating the movement generating function with respect to delta t1, delta tp, k1, k2, kp times respectively, and then putting t is equal to 0. So, again what we see is in the case of multivariate random vectors, movement generating function can be used to get the product movements. These are called the product movements because more than one variables are appearing over here, and we call them as product movements. So, one can get the product movements from MGF by differentiating them appropriately and then putting t is equal to 0. A few consequences of this result. So, under the assumption of result 1, let psi xt is log of mxt, where t belongs to minus a to a, where movement generating function is finite. Then, if I have to get expected value of xi to power m, what it says is differentiate mxt with respect to ti m times and then put t is equal to 0. If I have to get the variance, you look at psi xt, which is log of mxt, differentiate with respect to ti twice and put t is equal to 0 to get the variance of xi. Now, if one has to get covariance of xi and xj, then what it suggests is you differentiate this respect to Ti and Tj, and then put t is equal to 0. So, again what we see is this movement generating function can also be used to find the covariances. Now, the proof is very easy. This part follows from the last part by taking Ki is equal to m, Ki is equal to m, and Kj as 0 for j not equal to I. So, if you do that, you can easily see. So, Ki is m, all other Ki's are 0, so you got expect loop xi to power m. So, it says just differentiate with respect to Ti m times mxt and then put t is equal to 0. So, that is what the first result says. The second result says if you have to get a variance of xi, differentiate psi xt twice and then put t is equal to 0. Covariance, you can do this we have seen, the first assertion we have seen clearly holds. Now, let us look at the second assertion. So, I look at first differentiate with respect to Ti psi xt was log of mxt. So, that is 1 upon mxt partial derivative of mxt with respect to Ti. Now, let us differentiate this twice again with respect to Tj. So, del square Ti Tj. So, that means I have to differentiate this quantity with respect to Tj. Now, if you do that, you get mxt square, mxt del square del Tj Ti mxt, then del by del Ti mxt partial derivative of mxt with respect to Tj. So, now I put t is equal to 0 over here. So, thus for j is equal to I, if I put t is equal to 0 over here, mx at 0 is 1. So, that means here I put t is equal to 0. So, that is what you get, minus for j is equal to I, the two quantities are same. So, del by del Ti mxt at t is equal to 0 whole square, and mx 0 is 1. So, 1 square is denominator, I get 1. Now, this we have seen is nothing but expect loop xi square from the last result. This whole quantity is nothing but expect loop xi, because I am differentiating with respect to Ti and putting t is equal to 0, I get expect loop xi, and I take square of that. So, this turns out to be variance of xi. Now, I differentiate, I take t is equal to 0 over here for I not equal to j or I is equal to j, then I get at t is equal to 0 this quantity is 1. So, I get this at t is equal to 0 minus this at t is equal to 0, which is this, multiplied by this at t is equal to 0, which is this, and at t is equal to 0 mxt is 1. So, mxt square is 1. So, this is what is. And by the last result we have seen that if I differentiate mxt with respect to Ti and Tj and put t is equal to 0, I get expected value of xi xj. So, this becomes expected value of xi xj. This quantity becomes expected value of xi because I am differentiating mxt with respect to Ti and putting t is equal to 0. Similarly, this quantity becomes expected value of xj. So, this becomes expected value of xi xj minus expected value of xi into expected value of xj, which is nothing but covariance of xi and xj. So, movement generating function can be used to get covariances, variances, all product movements, provided movement generating function exists in a neighborhood of 0. Now, if movement generating function exists in a neighborhood of 0, that in fact guarantees the existence of or the finiteness of all kind of product movements. Now, let us do this result which says that we have seen that movement generating function is say of independent random variables is same as product of movement generating function. Now, this result is a converse of that result. It says let x1, x2, xp be a p times the random vector, and suppose their joint MGF is mxt, and suppose marginal MGFs are mxi. Suppose that joint MGF is such that it is product of marginal MGIs. Then one can conclude that x1, x2, xp are independent. So, if you observe that your joint movement generating function is such that it can be written as product of marginal MGFs, then you can directly conclude that x1, x2, xp are independent. In fact, this result 3 and the earlier remark 1 can be easily extended to the case of random vectors. So, for example, in this case one can say that if you these x1, x2, xp are random vectors and I look at their joint MGF, if joint MGF is same as product of individual random vectors, then the random vectors x1, x2, xp are independent. So, they have immediate or obvious generalizations to the case of random vectors. Now, let us talk about equality in distribution. We studied this concept in the case of real random variables. Now, here we extend that concept to random vectors in a straightforward manner. So, two p-dimensional random vectors x and y are said to have the same distribution if their distribution functions are same. Exactly the same way we defined equality in distribution in real variables. I say random variables x1, x2, xp are exchangeable if the distribution of x1, x2, xp is same as distribution of x beta 1, x beta 2, x beta p for any permutation beta 1, beta 2, beta p of 1 to p. So, what it says is I will call random variables x1, x2, xp exchangeable if the distribution of x1, x2, xp is same as distribution of any permutation of x1, x2, xp. So, let us see this result which is about equality in distribution. We did similar result in case of real random variables. So, let x and y be random variables having PMF or PDF fx or fy respectively. Now, if the PDFs or PMF are same for every x belonging to Rp, that would imply that x has the same distribution as y. So, if you see that a PDF of x is same as a PDF of y, you can directly conclude that x and y have a same distribution. Similarly, if x has a same distribution as y, then any function of x has a same distribution as the corresponding function of y for any function psi from Rp to R. Not only that, this result which has its analog in the real case, it says if the movement generating function of two random vectors matches in a rectangle around 0, then x and y would have the same distribution. So, I will not prove this result, slightly some of them are slightly involved. So, we will just proving those results over here. Now, let us see some applications of this. So, let x1, x2, xp are IID random variables with common PMF PID of f. Then x1, x2, xp are exchangeable. What it says is a collection of IID random variables is always exchangeable. Not only that, expected value of summation I is equal to 1 to p x1 upon summation I is equal to 1 to p xi is 1, provided the expectations exist. Also, probability that x1 is minimum of x1, x2, xp is 1 by p, provided x1 is absolutely continuous. So, let us try to prove them one by one. So, first I will prove that if x1, x2, xp are IID, then they are exchangeable. Now, to show that they are exchangeable, I have to show that x1, x2, xp has the same distribution as any permutation of it. That can be shown if I can show that the joint PDF of x1, x2, xp is same as joint PDF of any permutation of x1, x2, xp at the same point x. So, suppose that x1, x2, xp are IID random variables with common PDF f. So, let vector x is x1, x2, xp, vector y is x beta 1, x beta 2, x beta p for a permutation beta 1, beta 2, beta p of 1 to p. Then fxx, because they are independent, so it would be same as product I is equal to 1 to p marginal of fxi at the point xi. But so this is due to independence, but they all have a same PDF. So, fxi is same as fx. So, this is same as product I is equal to 1 to p fxi. So, this is due to they have identically distributed. But f of any xi is same as f. So, f of x beta I at any point would also be same as f. So, I can say that this is same as f of x beta I as xi. But that is nothing but PDF of x beta 1, x beta 2, x beta p at the point x1, x2, xp. So, what I get is joint PDF of x is same as joint PDF of y at every x belonging to Rp, and that is equivalent to saying that x has the same distribution as y by result which we did. So, what we saw is x1, x2, xp has the same distribution as any permutation of it. So, that means they are exchangeable. So, we conclude that if you have a collection of IID random variables, then they are always exchangeable. So, now let us do the part second, where I have to show that expected value of x1 divided by summation I is equal to 1 to p xi is 1. By A, we have for any permutation beta 1, beta 2, beta p of 1 to p, x1, x2, xp has same distribution as x beta 1, x beta 2, x beta p. So, that means any function of this would have any same distribution as psi of x beta 1, x beta 2, x beta p. So, their expected value would also be same. So, what I do is I look at here expected value of x 1 divided by their sum. That would be same as expected value of x beta 1, the first argument, divided by sum of all of them. This implies that expected value of x 1 divided by summation I is equal to 1 to p x I is same as, so I consider a permutation so that the first one is j. So, x j, but summation I is equal to 1 to p x beta I, whatever may be the permutation, is same as summation I is equal to 1 to p x I, because that amounts to summing all x i's. So, what I get is expected value of x 1 given summation I is equal to 1 to p x I is same as expected value of x j summation I is equal to 1 to p x I. So, that means in a sense this quantity does not depend on, so they all are same. But we also know that if I sum all these quantities, so that means summation j is equal to 1 to p x j upon summation I is equal to 1 to p, but summation of expectation is same as expectation of summation. So, I take that inside, so it comes summation j is equal to 1 to p x j, and this was a common factor everywhere. So, this is this, but this is 1, so expected value 1 is 1. So, I know that this does not depend on j and sum of all of them is 1. So, that means each of them has to be 1 by p. So, that proves the second part. Now, let us try to see the third part, C part, which is about finding probability that x 1 is minimum of x 1, x 2, x p, provided x 1 is absolutely continuous. Note that if x 1 is absolutely continuous and x 1, x 2, x p are independent, then joint random vector x 1, x 2, x p is also absolutely continuous. Straightforward to see. So, let x 1 p, x 2 p, x p p denote the ranked values of x 1, x 2, x p. So, that means x 1 p is the minimum, x p p is the maximum of x 1, x 2, x p. Now, these x 1 p up to x p p are called order statistics of x 1, x 2, x p. Now, since it is absolutely continuous case, probability of equality is 0. So, what we have is probability x 1 p strictly less than x 2 p less than x p p is 1, because x is x 1, x 2, x p is absolutely continuous. So, probabilities of equalities would be 0. So, now since x 1, x 2, x p is exchangeable, so probability that x 1 is equal to minimum of x 1, x 2, x p would be same as probability that x I is equal to minimum of x 1, x 2, x p, because I can replace x 1 by x I and consider the corresponding permutation. So, this gets replaced over here, but minimum of x 1, x 2, x p is same as minimum of any permutation of that. So, this would remain the same. But summation I is equal to 1 to p, probability x I is equal to minimum of x 1, x 2, x p is 1, because there are no equalities. So, one of them has to be minimum with probability 1. And what we saw is this does not depend on I. So, they all are same. So, that means each of them has to be 1 by p. So, that means probability x I is equal to minimum of x 1, x 2, x p is 1 upon p for I is equal to 1 to p. Now, before I conclude, let me give the following two take home problems. So, let x 1, x 2, x 3 be ID random variables with probability x 1 is equal to x 2 is equal to x 3 is 1 by 6, and probability x 1 is equal to x 2 less than x 3 is 1 by 6. Find probability x 3 less than x 1 less than x 2. Now, the second problem, which says x is x 1, x 2 be an absolutely continuous random vector with joint MGF given by this. So, these are joint MGF. What you have to do is you have to find the correlation between x 1 and x 2, and you have to derive conditions under which x 1 and x 2 are independent. So, take this as a take home problem. So, that was all about this module. Thank you for your patience and have a great day.